Section 8.5 of your textbook covers the topic of radical equations. A radical equation is an equation in which a variable appears in a radicand, or under a radical symbol. Radical equations are solved using the principle of squaring, which states that if a equals b, then a squared equals b squared. In practice, this principle means that we can solve a radical equation using the step of squaring both sides of that equation. However, it's important to note that this statement cannot be reversed. The principle of squaring does not imply that if a squared equals b squared, then a equals b. In other words, squaring both sides of an equation does not always produce an equivalent equation. So while squaring both sides of an equation can be useful in the process of solving a radical equation, it can also introduce extraneous solutions, which are not solutions of the original radical equation. To illustrate this fact, let's look at the two equations shown on this slide. First, let's consider the square root of n equals 3. By inspection, we can tell immediately that this equation has one solution, namely 9, because the square root of 9 equals 3. To arrive at this solution algebraically, we could use the principle of squaring. If we square both sides of our original equation, the square root of n squared is simply n, and 3 squared is 9. In that equation, n equals 9 also has one solution, the same solution as our original radical equation. However, at times, squaring will not produce an equation with the same solution. For example, look at the second equation. The square root of n equals -2. By inspection, we would notice immediately that this equation has no solutions. This is clear because the principal square root of a number represents the positive square root. So the square root of n can never be -2. If we were to try to arrive at the solution to this equation using the principle of squaring, squaring both sides, we would obtain n equals 4, which is an equation that clearly has one solution, 4. But this equation is not equivalent to that original radical equation. And we can see that this solution, 4, is actually an extraneous solution. If we plug it back in to the original radical equation, it does not make that equation true because the principal square root is not equal to -2. So we need to be careful with this process of squaring both sides, and we need to make sure that we are always on the lookout for these extraneous solutions as we solve radical equations. So what are the steps to solving radical equations? First, we will isolate the radical term. Second, we will use the principle of squaring to square both sides of the equation. Third, we will solve the new equation. But then fourth, we need to check all the possible solutions we've found in the original radical equation before we write the solution set. This is important because we might have introduced extraneous solutions by squaring both sides of the equation. Let's look at some examples. Our first equation is the square root of x minus 5 equals 11. Our first step would be to isolate the term containing the radical symbol. So we can add 5 on both sides to obtain the square root of x equals 16. Next, we can square both sides of the equation using the principle of squaring to obtain x equals 256. Clearly, the solution of that equation is 256, but we need to check to see if this is a solution of the original equation as well. So we'll substitute back in for x and consider the square root of 256 minus 5. Does that equal 11? Well, the principal square root of 256 is 16, and 16 minus 5 is equal to 11. So we know that 256 is a solution of our original radical equation, and so we can write the solution set. Let's move to example number 2. 2 times the square root of 3x equals the square root of the quantity 4x plus 16. In this case, there are 2 radical terms, but each one is isolated on its own side of the equation, so we can move right to using the principle of squaring and square both sides. When we square the left-hand side, be careful to square each factor. 2 squared is 4, and the square root of 3x squared is 3x. On the right-hand side, the square root of 4x plus 16 squared would simply be 4x plus 16. Note that we now have a linear equation. We can solve this equation by isolating the variable. And the solution of our linear equation is 2. However, we can't be sure that this number is also a solution of the original radical equation, because that squaring step means that maybe the linear equation is not equivalent to that radical equation. 2 might be an extraneous solution. So we need to check back in the original radical equation. Let's substitute 2 in for x. On the left-hand side, we would have 2 times the square root of 6. And on the right-hand side, we would have the square root of 8 plus 16, or the square root of 24. Now, if we express the square root of 24 in simple radical form, it would be equal to 2 square root of 6. So since this equation is true, that means 2 is a solution of the radical equation, and we can include it in our solution set. Now let's move to 2 final examples, both of which will contain extraneous solutions as we move through this process of solving them. Problem number 3 says the square root of the quantity x squared plus 8 minus x plus 4 equals 0. We'll begin by isolating that radical term. To do so, we need to both add x and subtract 4 on both sides of the equation. So we have the square root of x squared plus 8 equals x minus 4. Now we'll use the principle of squaring. In squaring both sides, we need to be careful. On the right-hand side, since we're squaring the binomial x minus 4, we need to use the process of binomial multiplication to do that. The result is x squared plus 8 equals x squared minus 8x plus 16. Continuing to solve for x, we can subtract x squared on both sides, and those terms will cancel out. Then we can subtract 16 on both sides. And finally, we can divide by negative 8 on both sides. So the solution of our new equation is x equals 1. However, we have to check to see whether or not that's a solution of the original equation as well. So let's substitute back into the original equation. The square root of 1 plus 8 minus 1 plus 4, and is that equal to 0? Well, the square root of 9, the principal square root of 9 would be 3. So we have 3 minus 1 plus 4. Is that equal to 0? Well, 3 minus 1 is 2, and 2 plus 4 is 6. Clearly 6 is not equal to 0. This means that 1, even though it is a solution of the equation that we obtained after squaring both sides, 1 is not a solution of the original radical equation. This means there are no solutions to that original equation. Our solution is the empty set. Finally, problem 4, the square root of the quantity x plus 7 equals x minus 5. In this case, the radical term is already isolated, so we can move right to the principle of squaring. And again, being careful on the right-hand side to square that binomial correctly. Note that after squaring, we have obtained a quadratic equation. So we'll solve this one by setting one side equal to 0 and then factoring the polynomial. Subtract x on both sides and subtract 7 on both sides to obtain 0 equals x squared minus 11x plus 18. Then factoring that trinomial, we have the quantity x minus 9 times the quantity x minus 2. And then setting each factor equal to 0 gives us 2 solutions for the quadratic equation, x equals 9 and x equals 2. However, these solutions of the quadratic equation might not be solutions of the original radical equation, so we need to check them both. Substituting back in 9 in place of the variable, we have the square root of 9 plus 7. Is that equal to 9 minus 5? Well, the principal square root of 16 is 4, and 9 minus 5 is also 4. So the solution of 9 is valid in the original radical equation. Let's check the solution of 2. Square root of 2 plus 7, is that equal to 2 minus 5? In this case, we have the square root of 9, the principal square root of 9, which is 3. That is not equal to negative 3. So 2 is not a valid solution of the radical equation. There's only one solution, so we write the solution 9 in our solution set.